I'm going to walk through problem 6-6 from the publisher solutions so I can give you some of the key points here. So the basic way to solve any of these truss structures, the first thing you should think about is trying to come up with the entire structure, do a free body diagram of the entire structure, and then use that free body diagram in your solve for the unknowns, the unknown reactions, is a good starting point. And that's usually what you'll have to do, but not always. There are cases where you have a situation where you can solve it without going through and finding the reactions. You could actually find the forces along the members. Because in general, what our problems will be is that you'll try to find a solution, either tension or compression, in each one of these members, right? So in this case, 1, 2, 3, 4, 5. We have 5, okay? So 5, and then each of them will determine whether or not they're under tension or compression. Okay, so this is some initial information that's given. All right. So the first part of this is we're going to look at the entire structure all together, and we're going to try to solve for these unknown. So right now you have a normal force acting off, normal to this surface. You have a reaction in the x direction and a reaction in the y direction. Okay, so that's one of the things to pay attention to, is like the whole object can have like a reactive moment potentially, where you can solve it for reactions, or you have a moment equation in this case. All right. When you're solving for individual joints, then there's no moment equation. There's just summation of the forces in the x direction, summation of the forces in the y direction. Okay. All right. So the first part here is just coming up with a free body diagram of the entire structure. All right. So in this case, like, you have your reactions here. Here's a force. Here's another force and another reaction. Okay, so you're going to have a total of 5 different forces, right? And you have 3 unknowns. Well, you can do summation of the moments about a point to use that to solve for an unknown. Summation of the forces in the x direction, summation of the forces in the y direction. So you have the 3 equations and 3 unknowns, so you can solve for those. All right. So looking at it first, the publisher, the author, chose to actually do a moment equation about A. And with that, when you do it that way, what happens is you eliminate these two, right? So you don't, because these forces are acting right at that point. So now you're just having the moment due to this, this, and this, okay? Okay, and how we come up with this equation, the first part is NC, that's this, the normal at point C, that reaction. And then it's times cosine of 30, 2 plus 2, because it's 2 meters here, 2 meters here, and it's the y component. It's this component right here. And what this does is, if you think about point A, this would cause rotation in the counterclockwise direction about A, okay? Or about a sense about A. Okay, now the next one is this one, due to this force, and it draw the line straight through, and you come up with 1.5 meters, 3 newtons. That would result in clockwise rotation, which is negative, about A, and then minus 4 times 2, which is just from here to here, and acting straight down, but doesn't really matter, that is down. It would cause clockwise rotation itself, so that's also negative, okay? So since this one and this one cause clockwise rotation about A, then they're negative, okay? And so it's very easy to solve for NC. All right. The next one is doing the summation of the forces in the x direction. All right. Now in this case, you're going to have AX, you're going to have the 3K, and you're also going to have the x component of this one. All right. So here's NC right here, right, or normal C. Then it's sine of 30 degrees because it is the opposite side here, opposite this angle. So this side, if you want to think about it, or up here, if you project it up here. Okay? And then minus AX. So in this case, we only have one unknown. Very easy to solve for AX. Okay? The next one Now we're going to look in the y direction. So here's one force in the y direction. Here's another force in the y direction. And then we have a force acting straight up here in the y direction also. So we have AY minus 4 because that's going down. And then 3.6 times, which is this force, right, the NC, 3.608 cosine of 30 degrees. So that now gives you AY, okay? So now we have the reactions at these points, at this point and this point, right? Okay, so we know those forces. We know the external forces acting on this body or this structure. All right. So that's when you did the whole structure. Now you need to take a look at the individual joints, okay? And you have some, you know, you could go through and have some choices here, but what you recognize is that if you do 3 of them, that will include all of the beams, okay? All right, so first thing is looking at joint C, all right, so over here. So the publisher or the author chose to do it over here to the right to start with, okay. So first part is looking at the forces here. And what you're going to see is that you could break it up in the x and y direction. There's no y component along this beam here, okay, or this member here. There's a y component along this one. And then there's a y component here due to this, okay? Now, one of the things you'll recognize here is that it follows the law of similar triangles. If you look at it, 1.5 and 2. So if you multiply this times 2 and this times 2, we got 3 and 4. So the ratio is it's a 3, 4, 5 triangle, so this is a 5, okay? Well, you can think about, well, this is 1.5, this is 2. If you calculated this, this would be 2.5, okay? So that's a 3, 4, this is a 3, 4, 5 triangle, 3, 4, 5 triangle over here also, right? So this is in the positive direction. Now, one thing when you go ahead and write this, of course you need the free body diagram to represent this, which I should have said first, but I didn't. But here it is. Over to the right, you have the free body diagram, okay? So the reason being is that when I looked at this, oh yes, which direction is it? Well, this was decided, the free body diagram was drawn with it going down to that point, okay? So it's negative, and it's negative because it's the y component, and it's going down, okay? So when we have to pay attention to, you know, the directions in terms of our x and y axis to determine that, okay? So it's going down. It'll be minus FCD, which is this force, and here's our 3, 4, 5 triangle, right? These are 3, 4, 5 triangles. Okay. So you just go and solve for this one, and you'll come at 5.28 kilonewtons. And it's under compression, okay? And the reason it's under compression is because that's the way it was drawn, all right? If you had gone and solved this and had it in the other direction, all you would have found out if you had this drawn off as a tension, and relative to this point, you would find this to be negative, then it would just tell you it's in the wrong direction, okay? So this gives us an indication when we actually go up and solve for at point D here, that we should draw it as a compression, okay? And that will make things easier. All right, so then now, summation of the forces in the x direction equal to 0. So what do we have? We have a component from here. We have, this is all just x, so that's what this is, negative in the negative direction, so it's negative FCB. And we have an x component here, which is be 4 over 5 times 5.208, which we found previously, and the minus 3.608, which is just the component here, and the direction is off to the left also, so this is also a negative. So this one's a negative, this one's a negative, and this one is a positive because the x component is positive. Okay? So you could solve for that. There's only one unknown. So now we have 2.36 kilonewtons. Okay? And it's under tension. How do we know it's under tension? Because that's the way it was drawn here. It was drawn as a tension. And since the answer came up to be positive, we know this is correct. Okay? So we'll use that. We'll use these directions when we go to the next, when we analyze the next point, okay? All right, so the next thing that the author chose, or the publisher chose, um, yeah, what you'll find is a lot of times, the authors don't necessarily go through and solve all these. It could be somebody else working for the publisher who solves them. So that's why you see a lot of differences in the approaches for the different types of problems. Okay, so here's the given, well, as I said, the given solution. Okay, so now looking at point A. So we already have two of them, FCB, FCD. Okay, so we're good with those. All right, so now doing the same thing at joint A. All right, now in this case, there's this one is defined as a tension. Okay, and we'll find that's going to make sense anyways because the other side is under tension. So we'll draw this one as a tension. FAD, well, we'll assume it's compression. In this case, the author drew it as compression, not knowing which it is yet. It doesn't really matter because you'll find as you go through, like I said, if it's positive, you got it in the right direction. If it's negative, it's not. And then drawing AX off to the left, okay? The reaction off to the left, okay? And that's what we had come up with originally, right? Because AX was positive. It was drawn off to the left, and it was positive, so we know it's in the right direction, okay? So, like I said, as you go through and solve it, anytime in your intermediate results, if they come up negative, what you should do is just reverse it, or next time you go to look at another joint, reverse it, and make it, if it was tension, make it compression. If it was compression, make it tension, okay? So it's easier to follow. So the point being is, you should, when you first start these, to select the directions of any of these, you can define them, you can make an assumption. Say, I think this is, this one's going to be compression, this one's going to be tension, this one's going to be, well, we know it's compression. Is to make some assumptions and just draw them out, okay? When you do the calculations from that point, what you should do is that if it turns out you know what it is already from that, the easier thing is just to draw it that way. Like in this case, we know this is off to the left. We know this is up because that's what we found here. We already found those. So we know that those are up. This is up. This is off to the left. We don't know what this one is necessarily just yet, although we can make the assumption that because on the other side, it was tension, so we expect this one to be under tension too. And then this one we don't know, but let's draw it as compression and start from there, okay? So the next thing is summation of the forces in the y direction at point A, okay? So it's 0.875, okay? That was given here. That was what we already found when we did the entire structure. And then minus FAD, 3 divided by 5, right? So it's the component here, the y component of this one, 3/5 times this, okay? So then you could solve for FAD. Comes out positive, so we know it's compression, okay? So the next one is summation of the forces in the x direction. AX, okay, which is 1.96. It's negative because it's going off to the left, right? The negative axis, negative direction in the x-axis. And then this one's negative because it's also going off to the left, and it's just 4/5 now because we're using the law of similar triangles here. And FAB is going off to the right, so that's positive. Okay, so we only had one unknown. We solved for that. And that one is under tension. How do we know it's under tension? It's positive, and it was drawn away from the point, so that means it's a tension. Okay, so now we have just one left, and it was chosen to be that point B was going to be the one that was done. So point B, FBD, which is just the this one member here, FBD going up, and then we have a force going down, and that's it at that point. Because there's nothing else, this has no y component associated with it, right? So it's simply just putting it in, FBD minus 4 equals 0. So FBD equals 4 kNewtons, and which is under tension, right? The last one was just a check. Okay, seeing that whatever's force is in this direction, so it's going to be equal opposite this one, right? So you can go and check that. So we find that FAB and FCB are the same, right? They're both, and they have to both be under tension. Okay? So two main parts you're generally going to find with these. You're going to find that, you know, you do the entire structure. When you do the entire structure, you're looking for the reactions. Okay? The reactions will be forces also. You won't have like a reactive moment at any of these connecting points because they're going to be on pin supports, right? Pins or rollers. Okay? Do that. Everything. Find the reactions. Then the next step, so the two main steps is use the method of joints to go around and solve the tensions and compressions in, or the forces of tension and compressions in those other members. Okay? So you like solve one, then you go to another one that's connected to it potentially, then you go to another one. In this one, it was chosen to be a little bit different order, but it works out fairly well. Okay, so this is a good problem to be able to work through. It's one of the earlier ones, so it's good. Okay, and that's it.